The air thrummed with a new kind of rhythm, not the slow turning of seasons or the predictable arc of the sun across the sky, but the relentless, mechanical pulse of a new age. In the sprawling, smoke-filled factories of the 19th century, amidst the clang of iron and the hiss of steam, humanity was unknowingly forging something far more profound than locomotives or textile mills. It was inventing a new kind of time. For eons, across diverse cultures and ancient philosophies, time was often seen as cyclical, a great wheel of perpetual return. Empires rose and fell, seasons spun, lives began and ended, only for the pattern to repeat. Time was a static backdrop, or perhaps a spiraling path, but rarely a linear, irreversible arrow pointing inexorably forward. Yet, as the Industrial Revolution roared into being, demanding precise schedules, synchronized production, and a rigid understanding of cause and effect, that ancient perception began to fracture. The very machinery that powered this new world, and the emergent science of how it worked, demanded a different truth about time. At the heart of this shift was a nascent field, thermodynamics. It was in this crucible of heat and energy that an Austrian physicist, a brilliant mind named Ludwig Boltzmann, began to unveil time's deepest secret. Around 1877, through equations and statistical mechanics, Boltzmann mathematically linked what we now call the arrow of time to a concept both elegant and terrifying: entropy. This was the universe's inexorable slide into disorder, a universal tendency for complexity to degrade, for energy to dissipate, for everything to spread out and cool down. Boltzmann's work revealed that the reason time seems to move only forward is not some fundamental cosmic imperative, but a statistical certainty. Scrambled eggs, for example, do not unscramble themselves. A drop of ink spreads out in water. It does not spontaneously recoalesce. This is not because some hidden force forbids it, but because the number of ways for things to be disordered is astronomically larger than the number of ways for them to be ordered. It is like shuffling a deck of cards. You will almost certainly never see the cards return to their original, unshuffled sequence through random chance alone. Boltzmann's insight, though initially met with resistance and ultimately leading to a tragic end for the physicist, irrevocably changed our understanding. Time, he showed us, flows in one direction because the universe is constantly, statistically, marching towards greater entropy. This redefinition had a profound ripple effect, seeping from the laboratories into the broader cultural consciousness. The question, can we travel in time, could only truly be conceived once humanity collectively accepted time as a one-way street, a river flowing in a single direction. Before Boltzmann and the Industrial Age, traveling back in time might have been akin to trying to move backwards along a circle. It simply led you to a different point on the same loop, without the inherent causality paradoxes we now perceive. The clatter of factory looms, the whistle of steam trains, the very need to track progress and output, fundamentally reshaped our species' understanding of causality and sequence, solidifying the idea of a fixed, unchangeable past and an unfolding future. This new linear understanding of time also fueled a profound cultural feedback loop. As science codified the forward march of time, a public appetite for exploring the past emerged. The rise of historical novels, meticulously recreating bygone eras, and the surge in archaeology, digging into the earth to unearth lost civilizations, were not coincidental. They were cultural manifestations of a newly ingrained scientific model of time, a craving to understand the fixed, singular trajectory that led to the present. We wanted to see what was back there on the timeline, because for the first time we truly believed back there was a distinct, unalterable place. But this thermodynamic arrow of time is also the first, and perhaps greatest, barrier to true time travel as we often imagine it. It is a statistical certainty on a macroscopic scale that makes the idea of reversing processes fundamentally improbable. This is where the concept of Poincaré recurrence time enters the discussion. This principle, derived from the study of dynamic systems, suggests that, given an infinite amount of time, a closed system will eventually return to a state arbitrarily close to its initial state. But the timescales involved are beyond staggering. For a complex system, say, a cup of spilled coffee to spontaneously reform in its mug, or for a room full of gas molecules to return to their exact, original positions, we are talking about timescales so absurdly astronomical they make the age of the universe, some 13.8 billion years, seem like an infinitesimally small fraction of a second. It is a number so vast it effectively rules out this path for backward time travel within any realistic cosmological framework. Time, then, is not merely a coordinate on a cosmic map like latitude or longitude. It is a dynamic physical process governed by the universe's most fundamental laws of probability, statistics, and decay. To travel against its current, to return to a previous moment, would demand nothing less than defying the universal law of increasing entropy. It is a challenge far greater than merely achieving immense speeds or bending space. This historical and physical context provides the essential groundwork for understanding why time travel is not just a technological hurdle, but a profound scientific problem, framing it as a battle against the very nature of cosmic evolution itself. The air thrummed with a new kind of rhythm in the 19th century, but by the early 20th, another, more subtle revolution was taking hold. If the relentless march of entropy, discovered by Ludwig Boltzmann, had seemed to slam the door shut on time travel, then the next great leap in human understanding was about to crack it open again. Just a sliver, but enough to ignite a firestorm of possibility. We had come to grips with time as a one-way street, a river flowing inexorably forward. But what if the river itself could bend back on itself, forming a powerful, swirling eddy? The story pivots now from the heat and chaos of thermodynamics to the elegant geometry of spacetime, and to the towering figure of Albert Einstein. His general theory of relativity, published in 1915, wasn't just about how gravity pulls things down. It revealed that gravity is, in fact, the very fabric of spacetime itself, warping and curving around massive objects, dictating how everything, including light and time, moves through the cosmos. For decades, this profound insight reshaped our understanding of the universe, but few realized it also contained the hidden, unsettling blueprints for a time machine. The key to this revelation came not from Einstein himself, but from an unlikely friendship forged in the quiet, intellectual halls of Princeton's Institute for Advanced Study in the late 1940s. There, the aging Einstein, a titan of physics, found a deep intellectual sparring partner in a brilliant but eccentric Austrian logician named Kurt Gödel. Gödel, known for his groundbreaking incompleteness theorems in mathematics, was far more than a logician. He was a master of abstract thought, and he turned his formidable intellect to Einstein's own equations. In 1949, Gödel presented a solution to Einstein's general relativity that sent ripples of shock and unease through the scientific community, including through Einstein himself. Gödel had devised a theoretical model of a universe that was slowly rotating. In this Gödel universe, spacetime was not merely curving gently around stars and galaxies, it was twisting back on itself so severely, so profoundly, that it created what physicists call closed time-like curves, or CTCs. These were not mere theoretical curiosities. They were paths within the geometry of spacetime that, if followed, would theoretically allow a traveler to return to an earlier point in their own history. Consider what this means. A journey along a closed time-like curve would not require exceeding the speed of light, which Einstein's own special relativity had famously declared impossible. Instead, it would involve navigating a specific, warped trajectory through this strangely twisted cosmos. Imagine charting a course through space and realizing that by following a particular loop, you don't just return to your starting spatial position, but also to your starting time. It is like sailing a ship around the world and finding yourself not only back at your original port, but also back to the exact day you set sail, ready to relive it. This was the startling, almost unbelievable implication of Gödel's mathematics. Einstein himself was deeply disturbed by Gödel's discovery. His elegant theory, a masterpiece of cosmic understanding, seemed to permit something he intuitively felt was a physical absurdity, a blatant violation of causality. The very notion that one could return to the past, even within the confines of his own equations, struck him as deeply problematic, a bug in the majestic machine he had built. Yet, Gödel's solution was mathematically sound, a legitimate interpretation of the general relativistic framework. Gödel's rotating universe was not the only theoretical spacetime to hint at time travel. Consider the interior of a rapidly spinning black hole, known as a Kerr black hole. The immense gravitational forces and the rotational drag within such an object are theorized to twist spacetime so violently that, for a hypothetical observer brave or foolish enough to enter, certain paths might lead back in time. Another powerful theoretical concept is the Tipler cylinder, proposed by physicist Frank J. Tipler in 1974. This is a hypothetical, infinitely long, and incredibly massive cylinder, spinning at an immense rate. Calculations showed that if you could somehow construct such a titanic object, its extreme rotation would drag spacetime around it, creating closed time-like curves that could allow a journey into the past. The crucial takeaway here is not that we are about to build a Gödel universe or a Tipler cylinder. The focus is on the startling, almost unbelievable revelation that the known laws of physics, as described by Albert Einstein's general theory of relativity, do not explicitly forbid backward time travel. In fact, under these extreme mind-bending conditions of warped spacetime, they seem to hint at its possibility. This stands in stark, dramatic contrast to the rigid arrow of time imposed by thermodynamics, which, as we have seen, screams an emphatic no to the idea of undoing the past. Here, then, we find the central, profound conflict of our story. the clash between statistical mechanics and its universal law of increasing entropy, which dictates an irreversible flow forward, and general relativity, which, through the whispers of its complex equations, suggests that time might, just might, be capable of looping back. This is why time travel, far from being mere science fiction, emerges as a legitimate, albeit deeply problematic, consequence of our most successful theory of gravity. It is a ghost in Einstein's magnificent machine, a haunting possibility woven into the very fabric of cosmic reality. The blueprints existed. Einstein's equations, twisted by the insights of Gödel, seemed to whisper that time itself could form loops, that journeys to the past might, in theory, be possible. But theory is one thing. The cold, hard mechanics of building such a thing, of forging a path through spacetime, demand an entirely different conversation. What is the true cost of a ticket to yesterday? To move from abstract geometry to physical reality, we must confront an almost insurmountable barrier: the universe's energy budget. Consider the concept of a wormhole, sometimes called an Einstein-Rosen bridge. These hypothetical tunnels through spacetime could, if stable and traversable, connect two distant points in space, and perhaps even two different moments in time. For decades, they remained a mathematical curiosity, a strange side effect of general relativity, dismissed as little more than science fiction. Then, in the 1980s, a renowned Caltech physicist named Kip Thorne began to take them seriously. His journey into the physics of wormholes began not in a sterile laboratory, but with a request from the legendary astronomer and science communicator Carl Sagan, who needed a scientifically plausible method for interstellar travel in his upcoming novel, Contact. This unlikely collaboration pushed Thorne and his students to delve into the intricate mathematics of these spacetime shortcuts. What Thorne and his team discovered was both thrilling and deeply sobering. To keep a wormhole open, to prevent it from immediately collapsing faster than light itself could traverse it, would require something truly extraordinary, a substance with bizarre, almost alien properties. They called it exotic matter, and its defining characteristic is a negative energy density, or even negative mass. Pause for a moment and consider what negative energy density truly means. Most forms of matter and energy exert a gravitational pull, meaning they have positive energy density. A region of space filled with exotic matter, however, would have a net energy less than that of a perfect vacuum. Think of it this way: a vacuum, devoid of particles, still has a baseline energy. Exotic matter would be like a hole punched in that baseline, a region that effectively weighs less than nothing, pushing space-time apart rather than pulling it together. This repulsive gravity is precisely what would be needed to prop open a wormhole's throat. The problem, however, is profound. Negative energy density appears to violate several fundamental energy conditions that underpin much of modern physics, conditions that ensure the stability of the universe as we know it. If widely abundant, it could lead to all sorts of cosmic paradoxes and instabilities, from perpetual motion machines to the complete breakdown of our understanding of cause and effect. Yet there is one place in the known universe where a form of negative energy density is not just theorized, but has been experimentally confirmed to exist: the delicate, elusive Casimir effect. This subtle quantum phenomenon was first predicted by the Dutch physicist Hendrik Casimir in 1948, and later verified in numerous meticulous experiments. Envision two uncharged, perfectly parallel metal plates, placed incredibly close together in a vacuum, separated by a distance often measured in nanometers. That is, billionths of a meter. According to quantum mechanics, even a vacuum is not truly empty. It constantly buzzes with virtual particles and quantum fluctuations, appearing and disappearing in fleeting existence. Between these two plates, only certain wavelengths of these quantum fluctuations can exist, those that fit perfectly into the narrow gap. Outside the plates, however, all wavelengths are permitted. This difference in allowed fluctuations creates a subtle imbalance, a statistical pressure that pushes the two plates together. It's an almost imperceptible force, yet it's very real, and crucially, it represents a region of space with a lower, or negative, energy density relative to the vacuum outside. While the Casimir effect provides a tantalizing glimpse into the reality of negative energy, it offers vanishingly little hope for aspiring time travelers. The amount of negative energy produced is minuscule, almost unimaginably small. It is localized to the tiny gap between the plates and cannot be harvested, collected, or shaped into anything that could support a macroscopic wormhole. To put it into perspective, the energy densities required to keep a wormhole open, even one barely wide enough for a human to pass through, are astronomically vast. To produce enough exotic matter, even if it were possible, one would need quantities almost comically large. Calculations suggest that the amount required could be comparable to the mass of the planet Jupiter, not just converted into energy, but somehow transformed into this bizarre state of matter with negative energy density. Jupiter, a gas giant, has a mass approximately 318 times that of Earth. Attempting to create such a colossal amount of exotic matter from a substance that may not even be physically constructible beyond fleeting quantum effects presents an engineering challenge that makes building a Dyson sphere or terraforming Mars seem like child's play. This is the sobering reality check. Even if the elegant geometry of spacetime, as described by Einstein's General Relativity, allows for the theoretical possibility of time travel, the brutal laws of quantum field theory and the ironclad principles of energy conservation erect a seemingly impenetrable barrier. The theoretical blueprints may exist, but the cost of a ticket to the past, the price of the exotic matter required to open such a portal, appears effectively infinite. For centuries, time travel has ignited our imaginations, fueling tales of heroic adventurers and dire warnings. But within those fantastical narratives lies a chilling possibility, the ultimate undoing. If one could journey to the past, could they not rewrite history, erase their own existence, or plunge the cosmos into an inescapable logical knot? This is the paradox, the single most famous obstacle to time travel, a concept that transcends mere philosophy and delves deep into the very fabric of physical reality. The question is not just if we can go back, but what happens when we do. The colossal energy requirements, the need for bizarre exotic matter, these are formidable barriers we have already explored. But even if a wormhole could be stabilized, even if infinite power was at our command, a more fundamental, more terrifying gatekeeper stands guard: the paradox itself. The most simplistic example, the so-called grandfather paradox, poses a stark question. If you travel back in time and prevent your grandparents from meeting, How could you possibly exist to make that journey in the first place? For decades, this thought experiment seemed to slam the door shut on any serious consideration of backward time travel, dismissing it as a logical absurdity, an intellectual dead end. But physics, it turns out, often finds elegant solutions where philosophy sees only contradictions. In the 1980s, a brilliant Russian theoretical physicist named Igor Novikov offered a profound reinterpretation. Novikov, renowned for his work on black hole physics and cosmology, formulated what he called the self-consistency principle. This powerful idea suggests that the laws of physics are inherently designed to prevent paradoxes from ever occurring. It posits that any event happening within a region of spacetime that permits closed time-like curves, those theoretical paths back to the past, must be locally self-consistent. Consider what this truly means. If you were to embark on a journey back to the 1980s, perhaps with the intention of altering a pivotal moment, Novikov's principle dictates that your actions, your very presence, were already part of history. They are, in fact, the predetermined cause of the future from which you originated. This makes paradoxes impossible by definition. You cannot kill your grandfather because if you had, you would never have been born to undertake the journey back in time. Therefore, some seemingly random occurrence, must prevent you. Picture the scenario. You arrive in the past, your mission clear. You raise the antique pistol, aim it at your unsuspecting ancestor. But then, the gun jams. Or perhaps, a sudden, inexplicable gust of wind knocks your aim off course by a mere millimeter. Maybe a banana peel, dropped by an unseen passerby, causes you to slip, losing your grip on the weapon. Or, in a twist that might feel like a cruel cosmic joke, you might experience a sudden, overwhelming change of heart, an unshakable conviction that this act simply cannot be done. The universe, according to Novikov's principle, is not actively censoring your free will in a conscious way. Instead, it operates on a deeper, more fundamental level, allowing only those solutions to the equations of physics that are intrinsically self-consistent. Only pathways that already make sense within the fixed tapestry of spacetime can physically manifest. This cosmic enforcement of consistency finds fascinating echoes in the quantum realm, the strange, probabilistic world that underpins all reality. In the 1990s, Seth Lloyd, a professor at the Massachusetts Institute of Technology, began to explore how time travel might operate on this subatomic scale. Lloyd's work introduced the concept of post-selection. In essence, he demonstrated how quantum mechanics might naturally resolve paradoxes by effectively allowing nature to veto any timeline that would lead to a logical contradiction. It's as if the universe, at its most fundamental level, runs a constant background check on all potential histories, discarding those that don't fit the established narrative. This reframe shifts our understanding of paradoxes from being a reason why time travel is impossible to a profound clue about how it must operate, if it is possible at all. It suggests that if journeys into the past are truly allowed by the laws of physics, then our universe must exist as a deterministic, block universe. In this view, the past, present, and future are not distinct, unfolding moments, but rather all exist simultaneously, laid out like frames on a cosmic film reel. Your journey to yesterday isn't changing history. It is simply part of history. an event that was always meant to happen, the cause of the future from which you came. This implies a deeply unsettling consequence. Free will, as we commonly understand it, might be an illusion, a subjective experience within a timeline that is an unchangeable, self-consistent loop. This isn't just a philosophical debate. It's a potential resolution to the logical contradictions that have long plagued the concept of time travel, providing a physical framework for how it could, theoretically, work. It hints that nature has built its own robust anti-paradox software directly into its operating system, ensuring that reality, no matter how strange, always remains coherent. Our relentless pursuit of time travel has often conjured images of gleaming, massive machines, of brave individuals stepping into a portal and vanishing into the annals of history. But what if the sheer scale of our ambition has blinded us to a more subtle, more profound possibility? What if the true secret to navigating the temporal currents lies not in sending an entire person, or even a vehicle, but in transmitting the most fundamental unit of existence itself, a single whisper of information? This radical shift in perspective invites us to abandon the colossal engineering challenges and dive into the bewildering, counterintuitive realm of quantum mechanics, where the very relationship between past and future becomes strangely entangled. Within this subatomic world, physicists have encountered phenomena that defy our classical understanding of cause and effect, experiments that appear to hint at a form of retrocausality, the future somehow influencing the past. One of the most famous and mind-bending of these is the delayed choice quantum eraser experiment, a concept first proposed by the visionary physicist John Archibald Wheeler in 1978, and later meticulously performed in laboratories around the globe. To grasp its essence, consider a single photon, a tiny packet of light. In the quantum world, a photon doesn't simply travel from point A to point B. It can behave both as a particle and as a wave, a duality that becomes apparent only when we try to observe it. When fired at a barrier with two slits, a photon acts like a wave, passing through both slits simultaneously and creating an interference pattern on a detector screen, a clear signature of wave-like behavior. But if we try to detect which slit it passed through, the photon suddenly acts like a particle, choosing one path and collapsing the wave pattern. The quantum eraser takes this paradox a step further. It sets up an experiment where a particle and its entangled partner are created. Entanglement means their fates are inextricably linked, no matter how far apart they are. If you measure one, you instantly know something about the other. In the delayed choice experiment, the particle is sent through a two-path setup, just like the double-slit experiment. Its entangled partner is sent elsewhere, to a detector that can be switched after the first particle has already made its choice of path. What scientists discovered was astonishing. A measurement made on the entangled partner today could seemingly determine the path the first particle took in the past. If the measurement on the second particle erased information about the first particle's path, the interference pattern reappeared, even though the first particle had long since hit its detector. This doesn't mean we can send a signal into the past to change history. A critical detail is that you need to compare data from both ends of the experiment to see this effect, preventing any true causal violation. Yet, it profoundly illustrates that at the quantum level, the boundaries between past and future are far more fluid and interconnected than our everyday intuition can fathom. This peculiar interconnectedness led to other radical ideas, such as the transactional interpretation of quantum mechanics, proposed by physicist John Cramer in 1986. Cramer's model suggests that a quantum event, like a photon moving from an emitter to an absorber, isn't a one-way street. Instead, it's like a handshake or a negotiation between a wave traveling forward in time from the emitter and a response wave traveling backward in time from the absorber. Both waves must agree on the properties of the event for it to occur. This bidirectional flow of information at the quantum scale paints a universe where the future isn't merely a consequence of the past, but an active participant in shaping the present. It's a universe where events are not just happening, but are being retroactively confirmed, a strange dialogue across the timeline. If the universe operates with such subtle, interwoven temporal connections, it begs a more profound question. What if reality itself is a giant quantum computer? Modern information theory increasingly explores the idea that information is not just something carried by reality, but might be fundamental to its very fabric. If the cosmos is processing information on a grand scale, perhaps a closed, time-like curve, that theoretical loop back in time permitted by Einstein's equations, isn't a physical wormhole to be engineered with exotic matter. Perhaps it's simply a bug, or a loop, in the cosmic code, an algorithmically permissible shortcut within the universe's own computation. This reframing opens up an entirely new avenue for time travel research, one that sidesteps the seemingly insurmountable energy requirements of macroscopic time machines. What if the goal isn't to send a human being, but to send a single quantum bit, a qubit, back in time? A qubit, unlike a classical bit which is either a 0 or a 1, can exist in a superposition of both states simultaneously, holding vastly more information. Theoretical models, explored by physicists like David Deutsch, propose that if such a quantum information loop were possible, it could be used to solve computational problems that are otherwise utterly unsolvable, even for the most powerful supercomputers conceivable. Imagine a computational problem so complex it would take longer than the age of the universe for a standard computer to crack it. But by sending a qubit through a hypothetical closed time-like curve, allowing it to communicate with its past self, the solution could become instantly accessible, the future whispering the answer to the past. This shifts the entire paradigm of time travel. It moves away from the brute force engineering of bending spacetime with colossal amounts of energy and towards the subtle, intricate processing of quantum information. If a genuine loophole exists in the universe's seemingly rigid temporal laws, it may not be found in the monumental gravitational forces that warp spacetime. Instead, it might be hidden in the deepest, most elusive logic of the quantum world, a whisper across time, not a roar. We have journeyed through the cosmic expanse, from the relentless arrow of entropy to the bewildering loops within Einstein's spacetime, and even whispered with the quantum realm about sending information across the timeline. We have chased the elusive ghost of time travel through the very laws of the universe. But what if the most extraordinary, most intimate form of temporal displacement isn't out there, in some distant galaxy, or inside a hypothetical wormhole? What if it is happening right now, within the confines of your own skull, every single day you draw breath? This chapter takes a profound, unexpected turn, veering sharply from the grand scales of cosmology and the perplexing rules of quantum physics to plunge into the intricate landscapes of neuroscience and cognitive psychology. Here, we argue that humanity's most frequent and personal encounters with time travel occur not in a sophisticated machine, but in the astonishing, often deceptive, internal workings of our own consciousness. Cutting-edge research from neuroscientists like Dr. David Eagleman, a renowned expert in the field, reveals a startling truth. Our perception of time is not a continuous, objective recording of reality, like a perfectly synchronized ticking clock or a seamless video playback. Instead, it is a complex, almost artisanal neurological construction, built piece by piece by our brains. Consider how your brain weaves together sensory data. What you perceive as the immediate present has, in reality, already been processed, filtered, and even edited by your brain a fraction of a second in the past. It is a post-dictive narrative, a story that your brain retroactively tells itself about what just happened, presenting it to your conscious mind as now. This slight, almost imperceptible delay means you are always, in a very real sense, living a tiny moment behind the actual unfolding of events, your brain carefully crafting the illusion of a continuous present. Perhaps you have experienced the peculiar phenomenon known as chronostasis. Recall the moment you glance at a clock, especially an analog one with a sweeping second hand. For a fleeting instant, that second hand seems to freeze, lingering in place for longer than a single second, before suddenly jumping forward. This is not a malfunction of the clock, but a direct, compelling example of your brain actively manipulating your perception of time. Your brain, in its attempt to create a smooth, coherent experience of reality, effectively stretches that initial moment, giving your conscious mind extra time to process the sudden shift in visual attention. It is a powerful illustration of just how malleable our internal clock truly is, a testament to the brain's subtle and pervasive influence over our temporal reality. Delving deeper into this internal time machine, we uncover the intricate mechanisms of memory itself. When you recall a past event, a childhood birthday, a conversation from yesterday, or a moment of triumph, you are not simply replaying a pristine video file stored neatly away in a mental archive. Far from it. Remembering is a dynamic, creative act of reconstruction, a process where fragments of information are reassembled, reinterpreted, and often subtly altered each time they are accessed. Every recollection is a fresh narrative, influenced by your current emotions, knowledge, and even your desires. This means your personal history is not a fixed, immutable record, but a living, breathing story that your brain constantly revises and updates, making your journey into the past through memory a distinctly imperfect, yet utterly vital form of time travel. This profound, innate capacity for mental time travel is deeply connected to the very root of our species' enduring fascination with the possibility of physical time travel. Why do we so desperately wish to revisit yesteryear, to alter the past, or simply to bask in nostalgic glow? These powerful human emotions, regret for past mistakes, the ache of nostalgia for bygone eras, the overwhelming desire to correct a misstep or relive a cherished moment, are not merely abstract feelings. They are fundamentally tied to the way our brain simulates past and future scenarios, a core cognitive function that allows us to learn from experience and plan for what is to come. Our longing for a time machine is, in many ways, an externalization of an internal process, an attempt to physically achieve what our minds already do, albeit in a subjective, non-physical sense. The brain's control over time perception is so profound that it can even be drastically altered by external factors. Consider how certain neurological conditions, such as Parkinson's disease, can subtly yet significantly distort an individual's sense of time's flow, leading to perceptions of events occurring faster or slower than objective reality. Even more dramatically, psychoactive substances, from caffeine to hallucinogens, are known to profoundly warp the subjective experience of time, making minutes feel like hours or entire days collapse into mere moments. These examples serve as powerful, real-world demonstrations of time's malleability within the human mind, showcasing that our internal clock is not a rigidly fixed mechanism, but a highly sensitive and adaptable system, prone to both subtle shifts and dramatic reconfigurations based on internal and external stimuli. The ultimate, breathtaking point of this exploration is to ground the often abstract, almost fantastical concept of time travel in the tangible, undeniable reality of human consciousness. While the quest for a physical time machine, capable of bending space-time and defying entropy, remains elusive and perhaps forever out of reach, our brains are already performing their own remarkable, if imperfect, journeys through time. Through the complex interplay of memory, which allows us to revisit and reshape our personal pasts, and prospection, which enables us to simulate and plan for future scenarios, we are constantly navigating our own personal timelines. This internal temporal navigation is not just a curious byproduct of consciousness. It is a fundamental process that shapes our identity, informs our decisions, and allows us to exist as beings aware of both what was and what might be. We have journeyed through the cosmic currents, from the relentless arrow of entropy that dictates the universe's slide into disorder, to the bewildering loops of spacetime hidden within Einstein's equations. We have probed the brutal energy costs of bending reality and confronted the universe's uncanny ability to self-correct, preventing paradoxes even at the quantum level. We have even found echoes of time travel within the very architecture of our own minds, where memory and anticipation weave our personal timelines. Now, as our remarkable exploration draws to a close, we must synthesize these threads to confront the deepest, most profound question of all: is time a fixed, immutable tapestry, or an ever-unfolding story still being written? This final inquiry brings us to two grand opposing visions of reality, two philosophical and physical paradigms that emerge from the deepest corners of modern science. The first is the concept of the block universe. It is a view strongly supported by Albert Einstein's revolutionary theory of relativity, which seamlessly merges space and time into a single, four-dimensional fabric known as spacetime. It is also bolstered by the self-consistency principles proposed by physicist Igor Novikov, which suggest that the universe inherently prevents paradoxes. In this profound model, the past, the present, and the future do not merely unfold sequentially. Instead, they all exist simultaneously, equally real, laid out across space-time like frames in a cosmic film reel. Consider a gargantuan, unchanging book. Every page, every sentence, every word is already written, from the absolute beginning to the ultimate end. We, as conscious beings, simply experience the illusion of reading one page at a time, creating our subjective sense of a flowing present. But the entire narrative, every twist and turn, already exists. If the block universe model is correct, then time travel to the past is not about changing what happened, for what happened has already happened. It is akin to moving to a different, already existing location on this vast spacetime map. Your visit, your actions, your very presence in that bygone era were always a part of its history, an indelible ink on one of the book's pre-written pages. You could no more alter it than you could scratch out a word from an ancient manuscript. This perspective offers a potential, albeit unsettling, resolution to the paradoxes that have long plagued time travel. You can travel to yesterday, but you can never truly change it. Yet, this fixed, deterministic vision is not the only game in town. There is another powerful paradigm, one of an evolving, open universe, where the future is truly unwritten. This view suggests that our current understanding of physics, while remarkably successful, remains incomplete. It posits that a final, unified theory, perhaps a grand theory of quantum gravity, which seeks to reconcile Einstein's general relativity with the strange world of quantum mechanics, might reveal entirely new principles governing time and causality, concepts that we cannot yet fathom within our current frameworks. Some theoretical physicists, grappling with immense problems such as the black hole information paradox, speculate that our very understanding of spacetime itself might be fundamentally wrong. What if spacetime is not the bedrock of reality, but an emergent property, bubbling up from a deeper layer of quantum information, much like temperature emerges from the chaotic motion of countless individual atoms? If this were the case, then the seemingly rigid laws of time might be far more flexible, far more open to reconfiguration than we currently comprehend. The arrow of time, the curvature of space, the very fabric of existence, could all be the result of a cosmic computation, a dynamic process rather than a static map. Our incredible quest to understand time travel, whether it is a journey to a fixed past or an unfolding future, has been profoundly fruitful. It has pushed the boundaries of human knowledge, forcing us to confront the deepest, most unsettling questions about the fundamental nature of reality itself. It demands that we grapple with the essence of causality. Does cause always precede effect? Or can the future indeed whisper to the past? It challenges our understanding of information. Is it conserved, destroyed, or can it loop through time? And perhaps most intimately, it confronts us with the enigma of consciousness. How do we, as sentient beings, experience this thing we call time, and what does that experience reveal about our place in the grand cosmic scheme? We are beings who are not just subject to time's relentless march. We are also, through our science and our wonder, beginning to understand its deepest, most guarded secrets. Whether the timeline is a closed book, its story already complete, or an unfinished saga, written moment by fleeting moment, the act of trying to read its hidden pages, to decipher its complex code, is precisely what drives science forward. It is what defines our unique position in the cosmos, as curious explorers, forever reaching into the unknown, forever seeking to unravel the echoes of eternity.